I'm going to talk about mining, sure, but also might extend a little bit and see if there's some relevance or connection to the automotive industry. I'd like to talk about some of the problems that we're solving. Also, why bother? Why would we bother solving these problems? And how exactly are we doing it? Because I think this is fitting, I wanted to start with some things in the news. Loblaws is actually committed to overhauling their truck fleet. Now they've just unveiled their first truck. They bought it from a Chinese manufacturer called BYD. It has about, marketing stated a 92-mile range. If you look into their literature, that looks like about 190 kilowatt hour battery. Of course, they're showcasing it in Vancouver. A lot of this technology is in temperate climates so far, and maybe we'll get into why that's happening. Something else that's happening this week, although this was a really exciting event. Also, Tesla is coming up with a semi-truck on the 16th. There isn't a lot of details actually about this. It's said that it's going to have a 200 to 300 mile range, but based on Tesla's best technology that I can find anything about, that's a 5,000 pound battery at least. Okay. So the reason I'm bringing that up is because there's a pretty big discrepancy between diesel and electric still today. So much so that Wired magazine said this, that electrifying highway trucks is a challenge on par and difficulty level with electrifying an airplane. So why would they say that? Obviously, it's an energy density statement. It's also a cost statement. So I read a little bit further into that article, and basically they're saying an 1,000 watt hour per kilogram battery would be required to basically put an airplane in the air with a battery electric. So I'm going to be a little bit cheeky here for a moment. I had a client call me about a year ago, and they wanted to electrify a plane. It's not exactly that, but actually, what I'm trying to do is prep you to think outside the box a little bit. So here's the client, here's the plane actually. So actually there are no batteries on board this plane. It's actually an electric winch powered by a battery. So they needed to achieve flight. It is a glider, of course. And the biggest requirement for energy is actually fighting gravity and taking off. So this is kind of old news. They've been launching gliders for a long time with winches. But in this case, they needed something portable. There is a power density in batteries now that you can actually hook this up to a high torque electric motor and perform this. Now that I've prepped you a little bit, now I'm going to step into the mining realm. What we see here is an open cast mine, but if you can imagine in the underground space that I'm mostly working in, that spiral would continue once they've taken enough of the overburden off or grabbed the ore that they needed nearest to the surface. We dig a hole and we just keep going until we followed the ore deep enough. So in comparison to the range anxiety that you have on highway, I have a different range anxiety, is that I have a very steep incline. It's a short distance, but I'm also carrying a tremendous amount of weight. Other problems is generally these things aren't paved. It's a gravel road, it's not well maintained. Also, it's cold or it's hot. And as we know, batteries don't like working in adverse temperatures. So here's the problem statement that I'd like to tackle today with you. Basically, it's ore haulage. So at the bottom of the ramp, we need to load some ore and we need to take it to the top of the ramp. The biggest underground truck is about 200,000 pounds gross vehicle weight. There's one maybe slightly bigger than that, but the other variable is just the distance, but a common grade would be 20%. So 20%. And actually I've mimicked this after a mine that we're actually producing something like this for, or we actually have equipment at. and it's called the Borden Lake mine, which is the all-electric mine for Goldcorp. But anyway, here's my problem. I need 240 kilowatt hours per trip, which is substantial. In relations to that Loblaws truck, that's a 90-mile truck pushing or pulling 80,000 pounds with a 190 kilowatt hour battery. I need it for one trip. So that's my problem. Why would I bother? Probably people have seen this image before. It'd be more relevant in the coal application because actually the canaries went in there if there was some methane being exhausted in between the coal seams. But, you know, it's also a health problem. If you've ever been underground in a mine, and although it's improved, it's like working inside the tailpipe of a city bus. It's terrible, especially overseas where there are less safety requirements. You're stuck underground, it's 30 to 50 degrees, and all you can smell is diesel fumes. So that's number one. I found some interesting journal articles on PubMed. They've been doing a lot of research and following what the health effects are and how you can tie that actually to lung cancer. So there are actually some cases now. So sure, EV is clean. That's a big benefit. Quiet, more efficient. There's a fuel cost difference. And we know on road, on highway, there really isn't a big enough fuel cost savings to warrant going and buying a Tesla at $80,000. But why underground mining? What's the real reason we're doing it in underground mining? I say that it's because it's cheaper to charge a battery than it is to run a fan. So obviously combustion needs fuel source, which includes diesel, but also includes air. This is a confined space underground. So we actually have to supply that air. And the further we go underground, the bigger the tunnel has to get and the deeper the tunnel has to get. So there's a major cost just in development, not let alone a 1,000 horsepower fan pushing that air underground. I'm just going to run a couple examples for you. So this is actually some information from the Goldcorp website. It is a company that we actually are supplying some of our EVs to. So Goldcorp Eleanor mine, which is in the far north of Quebec, for example, they require 1.2 million cubic feet per minute of ventilation. And what that relates to in cost, operating costs, is about 3 million liters of diesel fuel, 1 million liters of propane, and 35,000 megawatts of energy to run that mine. Something else, here's another mine. This is from Glencore. Okay, so it's an existing mine actually at Glencore, but the Onaping Depth mine is actually the next section underground, so they want to expand and go deeper and go after this new ore seam, which is really rich. When they first looked at it, though, it was just not economically feasible. It cost too much. And then they opened up the book again and said, what if we made it an electric mine? And basically what they came up with was something like $24 million in ventilation and cooling infrastructure costs that they could decrease. And that's partly to do with excavation. So they went from a traditional 5-meter heading down to a 3.5-meter heading, as an example. And they cut fewer ventilation passes. Now, also in that calculation is an increased cost for the mobile equipment. So EV still is a bit expensive, but the difference still warrants quite a bit of savings. So no-brainer, right? That seems like a lot of savings. And why hasn't it happened before? Actually, it has happened before. Just the mining process has changed. So what they used to do was run long headings with electric locomotives, with skips, everything more or less operated on electronics or electricity. until they started changing the mining method a little bit, and they required to do some excavations that were off of sort of a linear path. When they did that, the diesel machine took over. Now, obviously, there's something changing, and really what is that? Well, the technology did finally evolve in the battery realm. Lithium ion came on board. Why lithium? Well, it's got the some obvious things, greatest electrochemical potential. Let's step back a little bit. If you just look at the periodic table of elements, you can see it has the best potential for a metal, although there's a better energy potential in hydrogen just ahead of it. So I'll talk about that in a minute. But finally, lithium ion came on. It provided us enough power density to move the machines and also enough energy density to move the machines. Maybe not to make them fly, but definitely to move them enough that we can start doing work. So this is another statement that I'm going to make here, and it's that not all lithium batteries are created equal. I went to ConExpo last year trying to expand my network a little bit, looking outside of the mining space. And I walked around this big construction expo in Las Vegas, and there were a couple people dabbling in lithium-ion technology, but that's all they said. We have the greatest lithium-ion technology. Well, anyone who's done some research in this technology knows that there are a whole host of different chemistries. There are even a bunch of those chemistries that are mixed together that create all sorts of different power densities, cycle life. There's even substantial differences in the actual format of the cells and cost. And that's something that I face with actually as well in my industry. So there is actually quite a bit of different technology being implemented even in the mining realm, which is an incredibly small space. And I think that's mostly because there are a lot of different drivers. The automotive industry is really targeting energy density and cost. I'm not necessarily targeting those things, though I am also targeting those things. But because there's such a big return on investment in mining, I can either put that in my pocket or I can spend it on the best technology, or what I think is the best technology is a better way to put it. I'm sure there's a lot of smart guys here that know something that I don't know, but at least I'm focusing on something a little bit different. I can look at different chemistries, whereas Elon Musk really just wants to make the cheapest battery and the most of them. I don't care about that as much. I want the best, most interesting battery. For the layman here, here's just a comparison in energy density and cycle life of a couple of different chemistries. Also, the broad statement of 1,000 watt-hours per kilogram at the top. So we're still a long way from there of achieving electrified flight or a 900-mile on-highway truck. And to be honest, I've got a picture of a cool little car there that looks familiar, but you can't actually find any information about the actual, I can't anyway, about the actual Tesla cell, but it is somewhat relatable to the Panasonic 18650. They've put their name on it, it's branded differently, but anyway. But you can see that the NMC chemistry that they're using has one of the higher energy densities, but not a really high cycle life. I need to run all day, every day with my big truck. I need to charge it. Maybe I need to charge it every trip. So I need a lot of cycles, and one of the things I need to spare actually is the energy density. Why I think that the Tesla doesn't care so much about cycle life is because they actually limit quite narrowly the range in which you can discharge the battery. A really good article that tells me that that's true was when the hurricanes were hitting Florida, all of a sudden, all these Teslas had 20% extended range to get out of Dodge. Now, also an example of the differences in charge and discharge rates. LTO is one of the newcomers, not so new, but one of the newcomers that is available into heavy industry anyway. It has a very high C charge rate and discharge rate. There's a sacrifice, like I said before, when we need that big power or big charge, actually the sacrifice is a volume. So those batteries are actually quite large in comparison to an NMC or an LFP battery. So there are a couple of options there. We're working on sort of the industrial side where we're constantly charging, and that's where the LTO chemistry or the Nano, which is a brand name, which is kind of somewhere between NMC and LTO. Another thing that I'll talk about briefly that's a bit different in the mining side is the actual format of the batteries. So the Tesla or the Panasonic 18650, that's a cylindrical cell. That's a bit more common in the automotive space. I think that's an optimization of energy density because the anode and cathode are wrapped in that cell and then rolled together so that you can get the most dense battery possible. Whereas something that we use more frequently, which is the pouch type. And yes, we're again sacrificing energy density a little bit, but we're working in extreme hot and cold environments. So we actually want to be able to cool the entire battery. So that surface area is actually a key to the performance of our systems. And this is where this statement comes from, and that's that the thermal management is the key to the longevity and performance of the current lithium-ion batteries. Basically, like I said, we have the altitude, we have the heat. I've been in the mine underground, which was 52 degrees Celsius, and actually boiling water was coming out of the face. So it depends on the chemistry, but somewhere around 65, 70 degrees C, you have some runaway event in a lithium-ion battery. So that's critical to the safety and performance of our systems. An alternative method, which we've considered but discounted, is actually a swappable battery. And why I said we're discounted it is some people are using this in industry. There are people that aren't actually cooling the batteries. They're air-cooled systems that have a really low C or charge rate. So, if they need to charge it overnight, that machine can't sit there. So they need 3 batteries stacked somewhere, sitting there ready to go. So there's a big cost in having 3 batteries. And if you were ever to adapt that to a system that had thermal management, there are a lot of connectivity issues. So we've said that's not for us. I've got the hydrogen fuel cell here. A company did put a hydrogen fuel cell underground about 6 years ago. And the result was an interesting system, definitely, but CanMet, which is the group that monitors how much ventilation is required underground for a safety aspect or for venting exhaust, said that you needed 6 times more ventilation for a hydrogen fuel cell. Now that doesn't maybe compute because sure, fuel cells consume air or oxygen, but not that much oxygen. What the problem was is hydrogen's really sneaky. And if it ever escaped, you'd suffocate all of the people underground. So they actually said you need 6 times the ventilation to make sure that there's a safe atmosphere. So we're not going there. And wireless charging, my problem with it, and it may work in other applications, but talking about the heavy haulage piece, is that you need to put a lot of copper on your machine, thousands of pounds of copper on your machine to accept the other side of the charger. And so again, I'm losing payload, and if I lose payload, then I lose the usability of our machine. These PMAC motors And these battery systems, they have quite a high efficiency, way higher than a diesel engine. So these are approximate. I mean, certainly there are a lot of different aspects here that you'd have to consider on the efficiency of the two. But we got to make up the difference. Whatever that difference is, we need to use that to our advantage to make up the difference in the energy density lost in the battery versus a diesel machine. So where can we do that? PMAC motors, something that's probably touching the automotive industry in the same way, but the people that we're working with on electric motors, they sell a lot into China actually. And I don't know at what point it happened, but at some point in China, all of the big wins there, or anytime you got an incentive from the government, it hinged on how efficient your system was. So there was a drive there to increase, tiny pieces of efficiencies higher in the control of those motors, because that meant that they could win actually the R&D dollars and win the contract. So, 1% increase in efficiency doesn't seem like a lot, but there are people focusing all their energy on that. Maybe another problem that I have, sure, I have to have some control circuits that run different voltages of DC, but I also have a whole bunch of hydraulics, which are super inefficient. At least the traditional way of doing them is inefficient. So back to this statement again, ore haulage, 200,000 pound gross vehicle weight machine. About a year and a half ago, one of the key figures at Goldcorp said, if anybody has one of these machines, I'll buy it from you today. And this is a room with a lot of big company names. Nobody stood up, nobody said anything actually. And we went back to our facility and decided how we would do it and actually began patenting our process. Now, 240 kilowatt hours per trip results in almost 3,000 kilowatt hours a day. That's crazy. That's a lot of energy. Basically, we went, okay, there's only one way we can do it economically, and that's to drive it down to a single trip. So we have enough battery to do one trip, but we need to charge that battery really fast, because if we don't charge that battery really fast, we actually affect the actual carrying capacity throughout the day and how much payload we're pushing through the mine. So 12-minute charge, that's if we just charged completely the amount that we require to do the job. But we do have a bonus. We have to go back down the ramp, so we don't actually have to charge the whole battery. Because on the way down the ramp, sometimes we're actually carrying overburden or something to go fill one of the old voids. So we can actually recharge some additional energy on our way back down. So it does come with a complication. Here's an image of actually the conversion or the EV that we've done, okay? Quite a substantial battery pack in green at the front. But actually what I'd like to draw your attention to is the really fine print at the bottom. And it's basically two shifts, one on top, one on bottom. The traditional method, 8 hours of driving your diesel truck, 2-hour turnover, maybe a refuel, maybe lunchtime, I don't know. 8 hours of driving the truck again, 2 hours of refueling, what have you. But what we're doing is going for roughly an hour up our ramp, and then there's 15 minutes or 10 minutes somewhere in there that we have to charge, and we do it, we repeat it all day. Problem. The problem is Joe Miner doesn't want to take a break every 15 minutes or every hour. Well, maybe he does want to take a break. He probably definitely wants a break, but that's not traditionally how we've done work. So maybe we need to think about this a little bit differently. So that's actually an autonomous haul truck for a surface application. This is quite a bit bigger machine. But they are running these machines already in the oil sands and elsewhere. On surface, we're so accurate that when these first machines, this is rumor anyway, that they were driving on such an exact path that they actually dug their own trenches along that path and then got stranded in their own tracks. So anyway, with some work to be done, I think they've improved it substantially, just throwing an algorithm in there to confuse the path a little bit, make it more random. But I think ultimately an enabler of EV is also connecting to this autonomous thing. And definitely there are autonomous underground mines. There's a lot of different ways to do it, but sort of our focus is more an optical or a radar approach because GPS it isn't available underground. So, a matter of survival, strong statement. This is September 2016, just before a big mining expo. That's actually a McLean Engineering bolter. So that's the first electric vehicle that we did. And maybe this was the baby steps, because this machine used to be powered by both a diesel engine and electric hydraulic power pack. So it would drive to wherever it was doing its work, then it would plug in, and that would run off the electric pack. So baby step, like I said, we just needed it to do the battery or the tramming or the driving section on battery. And once it got to where it needed to work, it got to plug in and trickle charge as it did its work. We went a little beyond that. The customer wanted it to be able to also drill. There's a potential that this would go down into a heading that didn't have power, so it has more energy or more power than necessary to do a typical travel or driving. But that's evolved quite a bit now. We've done more machines. We're looking at this 40-ton or 200,000-pound truck. But some of, let's say, our achievements or what we're focusing our energy on, one is the thermal management piece, reduced charge times. Obviously, that's important on the automotive side too. Maybe not as important as what we're looking at. Efficient subsystems, and then finally the autonomous control piece. And you know, that Loblaws truck, I live in Collingwood actually. That's why Collingwood is on the map. So a 100-mile trip, you drop your groceries off in Collingwood from Toronto, and then the truck parks there overnight and charges, and then does its other trip. I don't think that quite achieves what Loblaws wants it to achieve. In fact, Quebec City isn't even far enough. So I think what we're working on may have some trickle-down effects into some other industries, but don't be afraid if you start seeing some really weird and wonderful trucks on the road going forward. And I just want to leave you with one more thing, and that's that, and I can't remember where I heard this, but definitely I believe in it, and it's that innovation moves at the pace of trust. So first, you know, us as engineers, we need to get trust in the industry before we're going to make these big leaps and bounds. Yeah, thank you.